Hello guys, how is it going? Today I'll be speaking on projector and projection onto subspaces under numerical linear algebra. My name is Isaac Amonote Yowetu. I'll be speaking on, we'll look at the problem of the day, which will throw light on the subject under consideration, which is projector and projection onto subspace. We'll look at a projection onto a line, which kind of throw light on the projection onto subspace. And then we'll look at projection onto projection matrices. And then finally we'll land on projection onto subspaces. This is the problem of the day. We have to consider the matrix A. And then the question is, what is the projection onto the range A? And the image under P of which of the vector 1, 2, and 3. Now let's have a graphical example. So assuming we are to consider the vector, this very vector here, and we want to look at the projection of this vector onto M, and assuming we have N also being a vector, we want to look at the projection of this same vector onto our M. So basically we want to look at the projection of the shortest distance onto M and the shortest distance onto our vector N. We'll look at this one from few examples. So our first example, assuming we have a vector V and a vector U, we have to find the orthogonal projector P onto the range U and the image under P of the vector V. Let's look at how to solve this equation. So what is the orthogonal projector P onto the range U, and what is the image under P of the vector U? Let's look at how to solve this. So to solve this, we would like to follow on the projection matrix such that our matrix P is equal to the P square, which we consider our P to be an idempotent matrix, and the matrix transpose is the same as the matrix itself. So since we are dealing with vectors, to find our P, we'll look at the vector P times the P transpose all over, to find our P, we'll look at what the vector V times the V transpose all over V transpose over V. So in other ways, we'll look at the outer product over the inner product. And then to find the projection of V onto U is the same as what our P matrix times V, which is expressed in this form. Now that we know the formula for finding our P matrix, which is the outer product over the inner product, we can now go ahead to solve our problem. So our outer product is U times the U transpose, which you know our U to be this and the E transpose is this. So the product of it is going to give us this very matrix here. This one times this, and this one times this, this times this, and this times this, which gives us the whole of this. And the inner product happens to give us this one times the whole of this. Since it's the inner product, this column vector multiply this row vector multiply the column vector to give us 2. Then eventually we happen to get our P matrix to be this, the outer product over the inner product, which happens to give us this matrix that we have here. We then want to look at the projection of V onto our U. So this is our matrix P. Once we know our matrix P and we know our vector V, we just multiply, and then we happen to get the projection vector. That is for minus 2.5 and then 2.5. Happens to know this one happens to give us a fair idea about what we are going to look at. So now, coming back to the problem of the day, we want to consider the matrix A again, or the question under consideration. So to solve this equation, and having knowledge about the first example, we now want to look at how to solve this problem of the day. So we want to here we are dealing with what? A matrix, not a vector. So we'll see how best to approach it. So now we want to still find a matrix P such that the P should be equal to the P square and the transpose should be equal to the matrix itself. So we want to consider our U to be a matrix A, which eventually we get at the projection of V onto our A to be the whole of this. But we need to take some few remarks here, such that we know we don't divide matrices. Hence, we will then like to fall on the inverse instead of the matrix division. And the point 2 is considering multiply the matrix A by the pseudo inverse to get our matrix P. All that we are interested in to get the matrix P. But to get this matrix P, we can fall on the matrix pseudo inverse, and our pseudo inverse is written in terms of this. And our matrix P, so to get our matrix P, we pre-multiply the pseudo inverse by A, the matrix A, to get our matrix P. So the first point, what is the first point is telling us is to get this thing back here. If this matrix is true, the inverse of this matrix is true, then we push this matrix here up here, such that we have our matrix A times what the inverse of this times the transpose, which is the same as multiplying A times what the pseudo inverse, which eventually gives us our matrix A, our matrix P. So now that we get our matrix P, we then want to look at how best can we solve this problem. A transpose times A happens to give us this matrix here, and then its inverse happens to give us this. So to find the pseudo inverse, we then consider the matrix A, the inverse of this times A transpose, which eventually happens to get this matrix over here. Then to get our matrix P, we now pre-multiply the pseudo inverse by this matrix A here. So but we happens to know our pseudo inverse to be this, which is the same as what we have here. And then the A matrix times the pseudo inverse happens to give us our P matrix. So this P matrix that we have here, the transpose of it will give us back our matrix. And the square of the matrix P will give us back our matrix again. So now that we know our matrix P, we then multiply our matrix P to our V, which gives us what the projection of V onto our A. That's pretty simple. So in conclusion, what we are saying is our P is the orthogonal projection onto the ring A, and the vector 2, 2, 2 transpose here is the image under P of the vector V. In example 2, we are to look at this very scenario here, or this very question here. It says let A be a two-dimensional subspace of R3 spanned by the orthogonal vectors U1, which is this, and U2, which is this. It says write the vector v, which is of this form, as the sum of vector in A, and then we have to find a vector orthogonal to A. Let's see how to solve this below. So to find the projection of V onto our A, then we look at what the projection of V onto U1 plus the projection of V onto U2. And it's the same as what finding a certain scalar times what U1 plus a certain scalar beta times what the vector U2, which the whole of this one happens to give us what the inner product, the inner product over the inner product happens to give us this scalar, and the inner product of this one over the inner product of this one gives us what this scalar beta here, and then we multiply with their respective what vertices, which this one is expressed as this, the whole of this one is expressed as this times our U1, which is this one, and the whole of this one is expressed as this, the inner product, and then with their respective what vectors. We continue with our solution. So we know the whole of this one gives us 2. If we multiply this one times this one, give us 2, and then the whole of this one gives us what? 1. And then the inner product of this one gives us 2, divided by the inner product of this one, which is 1. So 2 over 1 is 2 times the. So to get our vector x, the scalar 2 times the vector here plus the scalar 2 times the vector here gives us our 2, 2, 2. Then to get our vector v, which is orthogonal to A, we consider our vector v minus our projection matrix here, or the sum, our x here, our projection vector here. So our vector v minus our projection vector here to get what? So when you subtract it, then it gives us our projection vector, our vector which is orthogonal to what? Our A. So basically what we are saying is x is the sum of vectors v in A, and then vector v which is orthogonal to A is the whole of this here, this one here. So if you like this video, please like, comment, and then subscribe to this channel. Thank you.